Exactly. Right.
Okay, happy to introduce the next speaker, who is my colleague at UT Austin, Fernando Rodriguez-Villegas, who's going to talk about the geometry of character.
Okay, thank you. Thanks to the organizers for the invitation to speak. So, the beginning of the story I'm going to talk about goes back to Hitchin's paper in 1986 called The Self-Duality Equations on a Riemann Surface. He studied a two-dimensional reduction of self-dual Yang-Mills equations of mathematical physics. And a quote from his article: "We shall consider here solutions of self-duality equations defined on a compact Riemann surface, which I'll call sigma the surface." And says at some point, the moduli space I would like to thank the organizers for inviting me. All right, so the story begins with Hitchin's paper in 1986. Has to do with the reduction of a certain four-dimensional differential equation to two dimensions. And he finds that he could do this over a Riemann surface, which I'll call sigma as we go along. And he says the modular space of all solutions turn out to be a manifold with an extremely rich geometric structure. And you could say that again. It's been used, it's been now realized that it's related to the Langlands program, both in the geometric version and the arithmetic version. The most recent and more spectacular, perhaps, use is by Ngo in his proof of the fundamental lemma. So this modular space M is a smooth, non-compact, connected hyperkähler manifold. In very simple-minded terms, what it means is that it has several complex structures. So we can label them by I, J, and K, which satisfy the use of quaternion relations. And in one distinguished complex structure, I or minus I, this Simpson calls it the Dolbeau version of the space, and it parameterizes stable Higgs bundles. He did it in rank 2 and odd degree on the curve sigma. On all the other complex structures, it's a different variety, which Simpson calls the Betty version of it, and we can see that as parameterizing odd irreducible representations, so the fundamental group of the surface into SL2. So there's a little picture of the idea is that there's a whole sphere worth of complex structures on this manifold, and there's an action of the circle that sort of takes all complex structures other than I and minus I to each other and fixes I. So using the circle action and some methods in Morse theory, Hitchin computed the Betty numbers of this manifold. So let me show you the form of it. So if we denote by PTM the Poincare polynomial, so it's simply a placeholder for the Betty numbers, the dimensions of the cohomology groups of this manifold, it has this expression. So here our variable is G, the genus of the underlying Riemann surface. We're fixing SL2 as the group in question. So there's no point of trying to remember this formula, but I wanted to show it to you because the one thing I would like you to remember, this basic structure, is some polynomials raised to the power G multiplied by some rational functions of T. So it's a nice little exercise to convince yourself that this actually does give a polynomial for every G bigger than 1. So our approach, this is joint work with Thomas Hausel and Emmanuel Letelier, is to, instead of considering the Dolbeau version, the actual modular space of Higgs bundles, we consider its other incarnation, which is the Betti form of it, that is to say the character variety. And what we would like to do is get some information about the geometry of this variety, at least its topology, from counting points of this variety over finite fields, a well-used technique. Now, just to clarify, the Betti version of this manifold is diffeomorphic to the modular space of Higgs bundles, which ultimately perhaps is the more interesting variety. They are not isomorphic as algebraic varieties. They're really different things with an underlying same differentiable manifold. So, for example, the Dolbeau version, the actual structure of it as an algebraic variety depends on the complex structure on the curve, whereas the representation variety only depends on the topology. We only use the fundamental group. It's the only data that comes in. So let me describe then the character varieties that we will consider. So we take a Riemann surface sigma, genus G, and we take k punctures. So S1 through Sk are points on the surface. And we fix, so just take for the moment an arbitrary group G, and fix conjugacy classes C1 through Ck on the group, and consider this space M to be the representation variety, meaning all the maps from the fundamental group into the group G, where a little loop around each one of the omitted points gets mapped to our preferred conjugacy class. And there's a double bar there to indicate that we're going to take a quotient. So these are homomorphisms viewed up to isomorphisms, up to conjugation. And that requires a bit of a careful analysis to make sure that the variety M is a nice enough variety. But I'll probably not going to say a whole lot about it. But there's some care one has to do to define this quotient. So just to give you an example, example 1, let's say we're going to take, well, G is GLN of C, G is 1, the genus 1 curve with one puncture, and I'm going to take my conjugacy class to be a central element in GLN, and zeta n will always stand for a primitive nth root of unity. So this is a particular example. And as we will discuss more generally, since we're looking at representations of this fundamental group, we can use a standard presentation of the group to obtain the relations that are necessary to describe what it means to have a homomorphism from this fundamental group into any group. So here's the commutators of the two cycles A and B times the green cycle around the omitted point, so multiply to 1. So just to illustrate, it's kind of hard to describe these varieties in any kind of concrete sense. So I'll try to give you 2 examples where that can be done, but which are nice representative, but the whole zoo of these varieties is very difficult to give in any sort of concrete, explicit way. So, but here we can. So what does it mean to give a representation of this fundamental group? Well, we have to choose 2 matrices A and B and GLN, and their commutator has to equal zeta n times In. So as it turns out, this variety we can identify with C star cross C star, because up to conjugation, any pair of such matrices will have their nth power is a scalar, alpha and beta. And so given the choice of alpha and beta, we get a unique point up to conjugation. And this essentially is the uniqueness of the Heisenberg representation for the theorem of Stone von Neumann. So this variety is just simply C star cross C star in this case. Another example will be, let's say G is SL2 of C. The genus is 0, and we have 4 punctures. And we put around each puncture a class that is semi-simple. And again, here the group is reasonably simple. It's just a free group in 3 elements, or 4 elements multiplied to 1. What's quite nice, I'm going to show you a description of this variety. And as a number theorist, it's really pleasing to find this out, that this goes back to Fricke in 18 something or other in his book with Klein on the on automorphic forms. So I particularly like this version. So here's how it goes. So if you give yourself 3 matrices, right? I mean, the fourth one is just going to be the product or inverse product of the 3. So you're free to pick your 3 matrices. And declare these numbers AI to be the trace and Xi to be the traces, or sort of the complementary two others. And then Fricke discovered that there is this relation among these quantities. So there's some missing things to describe. I'll do that in the next slide. But the thing is, we're highlighting the x's as the variables here. So this is a cubic equation in the x's. And the thetas are we're going to view them as parameters. And, well, here's an explicit description of what these things are. The point is that what you get is that generically, as you vary your semi-simple classes, what you get is a smooth cubic surface in P2, and it has a triangle of lines removed. So here's my little picture of just 3 lines that meet in a triangle like that. Sorry? P3, thank you. Oops. All right, so what's the general story that I'm going to narrow in a more specific case of what we are studying in this work. So let's fix C1 through CK generic semi-simple conjugacy classes, and of type mu1 up to mu k, which by that I mean that these are diagonalizable matrices which have certain eigenvalues, and I want to record the multiplicity of those eigenvalues. So at puncture I have a matrix that has some eigenvalue repeated ui1 times, some other eigenvalue repeated ui2 times, etc. So the total number ui1 up to ui, etc. it adds up to n. So that's a partition of n, and we can always reorganize the mu's so that they're decreasing, which is the standard way to think of a partition. And so I'm going to consider a character variety with these choices of conjugacy classes. The variety itself depends on the eigenvalues, of course, but I'm going to drop the notation and simply write the variety as m mu hat. Mu hat mean the multi-partition of mu1 up to mu k. And I said the word generic, and I'll mention in an example exactly what I mean by that. Generic is more or less what you might imagine it means, but there's a precise way one can make that very precise. But essentially means that there are not going to be any multiplicative relations among these eigenvalues more than they should be. So here's a picture of the general story. Now genus G, we have the red cycles and the blue cycles, and the green cycles are the x's among the punctures, and the relation, the standard presentation of this group is this big relation at the bottom. So we can be fairly concrete as to what the variety is then. We have A1 through AG, B1 through BG, matrices in GLN, X1 through XK, elements in the given conjugacy class, and they're supposed to satisfy that huge matrix equation. So here's where we have to be more careful as to what exactly means to take the double bar quotient, but that's our variety. And if we take the conjugacy classes to be generic, then we could see that if it's not empty, which is not necessarily a simple thing to verify, the variety is a non-singular affine variety of pure dimension given by this huge expression there. And if anything else, this expression is fairly large. Already in the case of hitching, where n is 2, if you take genus 2, the variety is dimension 6. So already a very small case, it gives something that is hard to sort of work in the usual sense of certainly drawing pictures or any kind of explicit form of it. So let's go back to this example. Take one puncture, and the conjugacy class is n. So that means that we have one eigenvalue repeated n times. So that means that the conjugacy class is to be central. And if you look at the equation, any commutator of matrices will have determinant 1. So if you have a product of commutators and one other x that multiplies to 1, that determinant of x has to be 1. Therefore, if zeta to the n is not 1, the variety is simply empty. And so zeta has to be a root of unity, nth root of unity. Generic, in this case, precisely means that it's a primitive nth root of unity. And so if n is equal to 2, that simply means minus 1, and that's the sense in what very early on I mentioned Hitching discussed odd representation. So not quite representations of the fundamental group of the compact Riemann surface, but this twisted version, if you like. So in the genus 1 example, the example 1 that we talked earlier, the variety again is C star equals C star. So to obtain information about these varieties, we're going to count points over finite fields. So to do that, the group now is going to be GLN of FQ. And the tools we're going to use is Fourier analysis on this group G, some kind of heavy-duty combinatorics and symmetrics function theory, which I learned after giving talks about this several times that I should mostly stay away from explaining, because that's where people immediately go to sleep. But unfortunately, I have to do something to at least explain what the results are. All right, so I like to think of this as that doing combinatorics in this case results in geometry. So combinatorics can be geometry. So what's the strategy? So let's say just we have one puncture and we have one conjugacy class. If we think of the function that assigns to a conjugacy class the size of the number of homomorphisms divided by the order of the G's, so say a G finite group or GLN of FQ concretely, if you like. So this is a class function of G, and you can decompose it in terms of the irreducible characters of G. Okay, so that's what I mean by Fourier analysis. And this will be of some use if you can say something about that decomposition. And here's where we get this beautiful formula of Frobenius, which I call the mass formula. So say G is a finite group. Now it could be any finite group. Frobenius proved essentially in the same paper where he started the theory of representations of finite groups, where he defined characters and so on. He didn't quite do it in this generality. He did it for genus 0 and for genus 1, but we can forgive him for that. He could have easily have done it if he felt the need. So here's the expression. The number of homomorphisms of gamma being pi 1 of the surface into G, well, surface with the punctures, has this explicit expression as a sum of the irreducible characters of the group G. So you see a 2G minus 2 power and some functions associated to the conjugacy classes. These F's also, this is Frobenius notation, Frobenius notion. This is a sort of integral version of the basis. You know, it's a nice normalization of the values of the character. These numbers are integers, algebraic integers. So Now, so this formula has been used quite a bit by physicists and so on in the mirror symmetry context. It's my colleague Dan Fried and Quinn proved that this can be viewed as a version of the Verlinde formula for a topological quantum field theory. But in any case, here it is. And the beauty of it, we could do this for an arbitrary finally generated group gamma. There's going to be a Fourier decomposition. And the point is that if the coefficients of that Fourier decomposition are as complicated as the original quantity you're trying to describe, then you're not going anywhere. The beautiful thing is that this particular group gamma has this feature that the coefficients of its Fourier decomposition, so to speak, of this counting, has this particularly simple and explicit form. So what we can prove, and here I'm condensing about 50 pages of calculations that I purposely decided not to try to present, and I hope you're grateful for it. The variety M mu hat is polynomial count. I'll come back to that in a second. If I call the polynomial that does the counting E, that has an explicit combinatorial expression involving something called the whole little polynomials of symmetry function theory. I will come back to this and elaborate a bit more as to what all of this means. But just just a few words about polynomial count is what you imagine to be. You have a variety defined, say, of some number field, and you look at its reduction at various primes, and so away from some finite collection of characteristics, the number of points of this variety is a universal polynomial evaluated at the size q of the undefined field. Okay, so as a corollary, and here this is not entirely completely trivial to get this fact, but we proved in particular that if the variety is not empty, it's actually connected. Okay. And we do this by proving that the leading coefficient of this polynomial E is 1. Okay. And now for genus 0, that's a real tour de force, involving in particular a crazy inequality over the real numbers that we needed help from Gergely-Harkush to prove. So by a theorem of Nick-Katz, this polynomial E is what is called the E polynomial of the variety. Okay, so I'll explain what this means in the next slide. Ultimately, remember, the goal is to try to obtain some geometric information about the variety. At this point, well, we managed to prove that it's connected, which is not an obvious fact at all. But what else would you get from this fact? That you have an explicit form of the counting of points, and that counting is polynomial. Well, so to describe this, I have to mention the mixture structure. And this would be a very quick and brief description of what this is. So we can just take it as a black box. So the cohomology groups of this variety, the HM cohomology group of compact support, has a mixture structure on it, which amounts at the end of the day into a triple index series of numbers, Hij, M. And we put these three index numbers together in a sort of placeholder. This mixed-Hodge polynomial simply keeps track of what those numbers are. So what is this thing? We can view it as a common deformation of two other polynomials. The Poincaré polynomial would be if we just set x and y both equal to 1, and we're simply summing for a fixed m all the i's and the j's, and that just recovers the dimension of the space. And there's the E polynomial, which is what results by setting t equals to -1. So E stands for Euler. So this is a sort of more souped-up version of the Euler characteristic of the variety, which you would get if you set x and y equal to 1. But so you see the -1, what it does is sort of sums for a fixed I and j, an alternated sum over the various index of homology. So I like to think of this polynomial HC as sort of something that specializes to these two cases. Now, just a matter of notation, if it happens that the Hodge numbers are 0 unless the I and the j are equal, and so simply going to simplify the notation and use a q by replacing the x and the y by a root q. So basically, if I and j, if the condition holds, then the polynomial really is a polynomial in x times y, so might as well call that q and get on with it. All right, so a very, very simple example, just to be clear. So if you take a variety to be C star, then here's the calculation of this mixed Hodge compact support polynomial. And if you like, just look at the bottom. The number of points is q minus 1, which is what you get if you set t equals to minus 1 on the previous one. And that's the E polynomial of C star. So the thing about it is that if you really wanted to know the Betti numbers of your variety, knowing the E polynomial will not be enough, right? But it does tell you something. So if your variety is smooth and projective, and it happens to be polynomial count, then the count will exactly tell you the Betti numbers. But if the variety, as we have, is not compact, then what you get is this E polynomial instead.
Can you say what polynomial count means?
Polynomial count basically means that you have some variety defined, say, over a number field, and for every, so you take a model over some ring, a finitely generated ring, and if you look at all maps into finite fields, the size of the points of the variety through that base change is given by a polynomial in the size of the field. Now, standard examples of that phenomenon are, say, the Grassmannians and projective space. I mean, the many varieties that that are of interest that have this property. Of course, for a number theorist, in a sense, are the dullest variety you could possibly get, because there's absolutely no Galois representation of any interest in a way. But nevertheless, what remains, in a sense, is sort of the combinatorics of that polynomial. Okay. Now I have to, in order to be a bit more precise as to what is it that we've done, I have to introduce some more notation, and this, I apologize for the deluge of of notation here. So I will try to explain now So I'm leading towards a conjecture. So what happened was we computed the number of points of this variety over a finite field, and by basically staring at the result, we saw that there was a way to deform that result into something that is by adding an extra variable. And so now we conjecture that with this other extra variable, we actually have not just the E polynomial, but the entire mixed Hodge polynomial. So now I'm going to try to explain what is that expression for that mixed Hodge polynomial. Okay, so I'm going to define this huge gadget, omega zw, this genus G Cauchy function, and the sum lambda the sum is over all partitions lambda. So I'm going to explain the various pieces slowly. So first, let me explain this. Unfortunately, everything seems to start with an H. So there's zillions of H's meaning different things. H here stands for McDonald. These H twiddle here is a McDonald polynomial, which is neither a polynomial, although it was defined by McDonald. So this is a gadget that lives in lambda x tends to q qt. What's lambda? Lambda is the ring of symmetric functions in infinitely many variables. And as McDonald says, is not a function. But we have to call it something. Because this ring is sort of a limit of usual things where the number of variables keeps increasing. So tensor with qt means that the coefficients are going to themselves be polynomials in Q and T. So these polynomials have proved to be quite important for various aspects of combinatorics, and particularly connections for geometry, with geometry. And themselves are deformations of other things that were known before. So that's these guys over here. And you should think of this as starting to look like the Frobenius mass formula in some very highly many variable version. All right, so what's the other gadget? That other H lambda over there, ZW. So this is this thing. And this is a product over all cells of the partition lambda of this rational function. And A and L here stand for the arm and the leg length of the cell. And let me show you a little picture of what that means. So here's a partition in the standard graphical way to describe it. So this will be 1, 2, 3, 4, 5, 2, 2, 1. And for each cell, you draw the hook, which is this thing red and red, green and red. And the arm is the number of boxes to the right, which is 3 in this case. And the leg is the number of cells to the bottom, which is 2. So you take the product of all the cells in this partition of this rational function. And in some ways, which I still like to understand better, this thing that we take the product of, in a way, is like a caricature of the zeta function of the curve. And in fact, in a further elaboration of this, we will actually like to put in there the actual zeta function of the curve. But that remains to be seen exactly what it gets. Anyway, now I have I showed you the ingredients of this, what this omega is. And now what we're going to do is basically take this omega, which is a series, and write it as an infinite product. Now, in order to describe what that is, I'm going to use this capital log. But the point to get from this is that I'm defining out of this omega, a purely combinatorial thing, some a priori rational functions, both h mu hat zw. So let me explain what this is. So mu hat is one of the standard symmetric functions called the monomial symmetric function. And the capital log is this incredible device. It's called the platistic logarithm, which is simply a very powerful device to take products into sums, or rather to write a sum as a product. So what it does is, if you have a monomial of the form 1 minus m, if you have a term 1 minus m to the minus 1, where m is a monomial, then you assign to that the monomial. So, and it's multiplicative, so you take products into sums. So if something is an infinite product, then it takes you to the sum of the exponents. Anyway, so this is this guy, h bold mu hat, which a priori is a rational function in ZW. All right, so finally I can tell you what the conjectures are that we make. So first of all, this thing is, we claim, or we conjecture, is a polynomial, which is of degree d mu hat. D was the dimension of the variety. And it has, after changing z to minus z, has non-negative integer coefficients. The Mix-Hodge polynomial of the variety m mu hat is a polynomial in x times y and t, and is independent of the choice of eigenvalues as long as they are generic. And these two are connected in this way. So it's hard to keep track of all these changes of variables, and I'm just sticking to what we have. But if you want, the thing to keep from this perhaps is that this purely combinatorially defined gadget h bold mu hat essentially is the Mix-Hodge polynomial of the variety m mu hat. Okay, so we deduce from this a few consequences. So the McDonald polynomial satisfies a symmetry, which translates into these omega functions behaving like this. You switch C and W, it remains the same. You change the sign, it remains the same. So what that means is that the H mu hat satisfy the same property. And you get this strange conclusion that if our conjectures are true, then we should also have this property about the mixed-Hodge polynomial. And this is what you expect. This will be exactly Poincare duality for a variety that was smooth and projected. So what this implies, or this suggests, is that the varieties mu hat satisfy Poincare duality even though they're not projective. They're not compact. Okay, so that's a far from clear fact as to why that should be the case. So let's look at some examples. Some of the conclusions of this conjecture are completely combinatorial. So let me give you some examples of this. So for example, if you take genus 0 and k is equal to 2, then it's a very simple matter to see what you're trying to calculate. The variety itself is a very simple thing. And you find that the variety is a point if the partitions are just 1 and 1 and is empty otherwise. You just can't get anything generic for other cases of the partitions. So what you get is this identity. And this is actually known. This is called the Cauchy formula for Macdonald polynomials and was proved by Garcia and Hyman. So from our point of view, the formula Cauchy for Macdonald polynomials amounts to the statement about the variety up here, that it is a point in that case and is empty otherwise. So we look at genus 1 and k equals 1, and the partition is n, so the class is central. Then we already seen that the variety was C star cross C star, so we certainly know the mixed Hodge polynomial of that. And we put the two things together, and in place this massive identity. And I put a question mark because it's a consequence of the conjectures, but we, well, apparently there is a proof, but I'm not completely convinced that I believe it. But anyway, this massive thing is this statement that the variety mu hat is C star cross C star. And you can just check both sides on the computer up to whatever order you have managed to do, and it certainly works. Okay, another example, it was example 2, that was P1 minus 4 points, the case of the cubic surface minus the 3 lines. So in this case, you work through your description of what this H was, and you find that it's E squared plus 4 plus W squared. And this matches with the concrete calculation directly from the fact that this is a cubic surface minus 3 lines with a bit of some combinatorics of how these mixed Hodge structures work. You also find that this agrees with the previous statement. So, for example, concretely, the mixed Hodge polynomial of this open cubic surface is this. So let me give you some more examples, but these are examples of what the conjecture predicts, not examples of things that we can prove. So for example, let's take genus 0 and now take 6 punctures where we put an n, so we put a partition n minus 1, 1, so it would be sort of a, if we were allowed to use any eigenvalues, it would be like putting a reflection, but the eigenvalues have to be generic, so it's something that has one eigenvalue n minus 1 times and then another eigenvalue at each one of the punctures. And let me display the coefficients of this thing in a grid where I'm going to put the coefficient of z to the 2i, w to the 2j in the spot ij. It's a polynomial in c squared and w squared, so I don't lose anything that way. So if n is 1 or 5, we get that. If n is 2 or 4, we get this. And if n is 3, we get that. And just for the sake of experiment, does anybody find any patterns, any more hidden patterns than just more or less obvious ones, which you can see the symmetry that I mentioned. The sort of Poincare duality here translates on the obvious thing that you can flip these things around. But there's somewhat more hidden feature here, which I don't know if anybody can spot. Not to mean to put anybody on the spot, but no. Well, the numbers 1, 26, 66 are other well-known numbers. So they're called the Eulerian numbers. Anyway, back to the case of Hitchin, which was n equals to 2, and a partition, a central class. So here, there's another feature of this varieties is that the center of the group, C star, acts on each one of the A's and the B's, because you can just scale them, and that sort of doesn't show up in the commutator. So there's an action of C star to the 2G on the variety, and you can take the quotient by that and get this variety mu hat twiddle, which is really ultimately what Hitchin was studying. So that translates into the fact that the polynomial h mu hat zw has to be divisible by z minus w to the 2G. And again, that's sort of conjectural, given that we don't know exactly that this is connected to the Mish-Hodge of mu hat. So here's what you get for n equals to 2. And so you see the shape of the formula is like the one for that Hitchin had. These are rational functions, coefficients times polynomials to the 2G. And so, in fact, for n equals to 2, we can prove all of the conjectures, basically by some heavy-duty geometrical arguments that my collaborator Hausel had studied the cohomology of this variety in detail, and could use that to prove all that we claim for this case. And just as a check, the Poincaré polynomial of the variety in the case of Hitchin agrees with the one we get from ours. Now, I should emphasize that Hitchin was doing is working on this Dolbeault version, which is a completely different algebraic variety that has the same underlying one, and using completely different methods, the circle method, which is something totally different from the Weil conjectures. And we're using sort of this other algebraic version of the variety and using the Weil conjectures, or rather some sort of extension of them, this deformation with another variable of them, and so it's satisfying to know that they agree. All right, so finally, here's an explicit form of the result that I mentioned. So the E polynomial of mu hat, that is the polynomial that does the counting of points, has this precise form. So here's an explicit version of what I wrote earlier in terms of this h mu hat. So in this particular specialization, where the first variable is replaced by root q and the second one by 1 over root q, the polynomial h mu hat, the rational function m mu hat is a polynomial in particular. Okay, so in other words, the conjecture 3, the part 3 of the conjecture is true if we replace q and t by q and minus 1. So the E polynomial part of the conjecture agrees, but it's sort of putting the thing backwards because this is where we started from, and we went back to the conjecture from here. So another version of the Curious-Poincaré duality is that this polynomial is palindromic, so it reads forwards and backwards the same, which again is something not completely obvious from just knowing that this is the polynomial that counts points on this variety. All right, so let me move to one other aspect of this, which is the connection with quiver varieties. And this is going to be faster than I had before, to condense what I want to say in the time I have. So by a quiver, I mean a directed graph, although here's not directed, but at the end of the day, the actual choice of orientation doesn't matter very much. So here's an example. So it's a graph that is allowed to have loops, and it's allowed to have multiple edges as well. So these quivers, one studies are representations of it. So what's a representation of this quiver? Is something like this. You attach to each node a vector space, and to each edge you attach a map, a linear map between the corresponding vector spaces. And you declare things to be isomorphic in a somewhat obvious sense. You can define a direct sum of representations. And the thing that I want to record here is the dimension vector alpha, which is simply the dimension of the vector spaces that we put at the edges. Okay? And so Victor Katz proved that if you look at the representations of a quiver over a finite field FQ, so in order to make a meaningful count, you want to count things that are absolutely indecomposable. So what I mean by that is that even after passing to the algebraic closure FQ, the representation doesn't break up as a sum of two others. So he proved that if you count the number of absolutely indecomposable representations of a given quiver, that's given by a polynomial, and now called the sort of a polynomial of the quiver. The polynomial depends on the choice of, so you fix the dimension vector and you count, and then you get a polynomial a alpha as a q. So he already anticipated this. He proved that this quantity that counts the number of absolutely indecomposable representations is a polynomial a. So let me give you a very simple example, but I think it's illuminating. So take the Jordan quiver, and you'll see why it's called the Jordan quiver in just a second. So simply one node and one loop. So here alpha is simply a number, which is the dimension of the vector space. So what is a representation of this quiver? It's simply a map from a vector space of dimension alpha to itself. And isomorphism classes of such things are simply maps of this sort up to conjugation. And we know how that works. We can analyze them by means of the Jordan decomposition theorem. And if you think about it, you see that to be absolutely indecomposable simply means that this map has to be one full Jordan block of that dimension. And so you have one choice left, which is the eigenvalue that you can choose. And so you want to be indecomposable in FQ bar. It has to be one block with an eigenvalue A in FQ. So there's Q of those, one choice for each eigenvalue. So this polynomial, in this case, simply Q. So attached to our data that define these character varieties, we can associate to that a star-shaped quiver, which is it star-shaped or crab-shaped. So there's G loops attached to a central vertex, G being the genus of the Riemann surface, and there's a way to encode the multiplicities of the eigenvalues in this combinatorial way. So basically, these are the partitions are the differences between one and the next. So I'm just giving you a bit of a recipe that, given the data that define this character variety, there's an associated quiver with a given associated dimension vector. And so what we proved also is that if we take the same h mu hat that we defined before in a purely combinatorial way, and you specialize it in this other form, you set the first variable to 0 and the second one to root q, you precisely get the polynomial that counts the number of absolutely indecomposable representations of that associated quiver. So this other specialization also has gives us a result, a polynomial. So further evidence that the h mu hat itself is a polynomial. So this suggests a relation between the cohomology of a associated variety. So Victor Katz's polynomial counts the number of absolutely indecomposable representations of the quiver, but associated to that quiver there is a variety, Q mu hat, which has that number of points. And I'll describe at the very end what that variety, how to describe that variety in our situation. So this related quiver variety, it has the same dimension as mu hat. It has polynomial count, namely the count is the a polynomial of the quiver, but in fact has pure mixed structure. And so what this identity suggests is that, so we have to go back and see how this polynomial is related to the compact support mixed Hodge polynomial. But doing the specialization 0 root q precisely picks out of the mixture structure the pure part. The pure part meaning the pieces that have I plus j equal to m. If you had a smooth and projective variety, that would be the only thing you have. So a way to describe this statement of the equality of two polynomials is to say that the pure part of the Mix-Hodge polynomial of the character variety equals the Poincaré polynomial of the quiver variety. And so this is a fact that just comes about from the calculation of both sides, but we, of course, like to interpret this in a geometric way and think that the two varieties are related in a particular way that results in this fact about their corresponding counts. So there's also a completely different aspect that I didn't mention, which the same A mu hat Q is associated to certain multiplicities of characters in GLN of Q. This is more of the aspect of the story that interests my collaborator, Emmanuel Leterrier. Anyway, let me just finish with this fact. If you combine all of these conjectures together, you find the following fact, that the polynomial A mu hat evaluated at Q equals to 1 should equal the middle Betti number of M mu hat. And this is now a concrete, simple statement about the variety M mu hat. And since this is a topological statement, it's also the statement about the middle cohomology of the modular space of Higgs bundles. So let me give you an example. So if you look at the example I wrote before, the setting one of the variables to 0 gives us this. So I'm thinking of this as 166 plus 51q, 22q squared, and so on. Now, because it's symmetric, the value of 1, which is the sum of these numbers, is the same as the sum of these numbers, and that's the dimension of the middle cohomology. So this is what we expect to happen. And let me finish with a description of this quiver variety, which is has a very similar flavor to the character variety, but in an additive form. So you give yourself adjoint orbits now in the Lie algebra in matrices. And again, you prescribe the multiplicities of the eigenvalues, so semi-simple classes. Now, there's a technical thing here that we need to assume that the mu hat is indivisible, so there's no common factor to all the entries to guarantee there exists a generic choice. And then you define Q mu hat as essentially the same version of the character variety, but now in an additive form. So here the brackets now mean simply the Lie algebra bracket, so AB is AB minus BA. And here the A's and the B's are matrices in GLN of C in the Lie algebra, and the C's are in the given adjoint orbit. So this is a concrete description of the quiver variety, and it's very tempting to imagine that we have a multiplicative version and an additive version, and then we can go from one to the other by taking the logarithm. And that is certainly tempting, but that's as far as it goes, at least for the moment. But certainly, somehow this should be a sort of infinitesimal version of the character variety, and that should go some ways into explaining why their cohomology should be related, as we see by this counting procedure. All right, well, I'll stop here. Thank you. It's a GIT quotient.
Right, so but you get an affine variety, for example, so do you just take spec of the...
Yeah, of the fixed function.
And so do you have any relation with something, so you can make some sort of Nakajima quiver varieties?
This is an example of Nakajima quiver variety.
And so there the quotient is really...
Yeah, this is a more sophisticated quotient. Yeah, it's some whatever it is. Yeah, it's a more sophisticated kind of quotient. Yeah.
So this in particular is going to be projective over some affine.
Maybe. I don't. I don't know much more about the variety. That is it's certainly smooth as much as I think I know, and it has pure mixer structure, which is already very different from the other case, right? So in this kind, counting is all you need to do.
Any other questions? So let me remind you that we have a coffee break now, and then at 3:30 we resume.